Now, if you're an on-site maintenance tech or a reliability engineer, you already know the classic drill, right? You walk the floor, check the operating temps, and most importantly, you listen for the grind. That squealing, that rumbling, it's been deeply ingrained in our maintenance culture as the ultimate red flag. But today we're going to challenge that entire habit. We're breaking down the actual physics of why a perfectly quiet bearing is very often a stealth threat. We need to transition from just listening to actually measuring.
Okay, so here's our agenda for this masterclass. We'll cover the hidden cost of silence, why our ears fail us, electrical erosion versus false brittling, the lambda ratio, envelope versus acoustic emission monitoring, and finally, your new predictive protocol.
Let's jump right into Section 1, the hidden cost of silence. To kick things off, let's just face the executive reality here. A quiet bearing is often a threat right on the verge of causing massive downtime. By the time a failing bearing actually starts making a noise you can hear, it is almost always in the final stage of death. And because we waited for that audible symptom, we're not just replacing a simple bearing anymore. The secondary collateral damage to your shaft journals, the bearing seats, the seals, the couplings, it multiplies the total repair cost by 5 to 20 times the cost of the bearing itself. Literally, 5 to 20 times. Relying on silence is just costing us an absolute fortune. Moving on to Section 2, why auditory checks fail.
So why exactly can't we hear the failure coming? I really want to ask you this directly to challenge those daily physical route checks you do. Why on earth does a dying bearing sound perfectly healthy? It goes against everything our intuition tells us about heavy machinery, doesn't it? But the answer actually lies in the physics of subsurface fatigue and where that damage really starts at a microscopic level.
Let's map out a bearing's failure through these PF curve stages. Under cyclic Hertzian contact stress, the maximum shear stress doesn't happen right on the surface. Nope, it happens at a depth of roughly 0.47 times the Hertzian contact half-width. For a typical bearing, we're talking about 0.1 to 0.5 millimeters below the surface. In stages 1 and 2, microcracks initiate and propagate completely parallel to the surface. And because the rolling contact surface remains perfectly intact and smooth above it, there is absolutely zero mechanical impact, which means zero noise.
This brings us to a crucial point. Based on ISO 281 L10 life calculations, that silent crack propagation phase represents 80 to 90% of the total bearing fatigue life. Think about that. If you are relying on manual auditory checks, you are flying completely blind for up to 90% of the failure timeline.
All right, Section 3, electrical erosion versus false brittling.
There are two highly specific, completely silent killers that you probably encounter all the time out on the floor, but you'll rarely ever hear them coming. Both of these bypass the surface impacts needed to make noise, but they do it in totally different ways. First, we have electrical erosion, which is heavily driven by variable frequency drives. Street currents above 0.5 volts AC causes continuous micro-arcing. It evenly distributes damage, basically melting these microscopic craters to just blend right into the background noise. Then, on the flip side, we have false brittling, which happens in stationary equipment. Tiny micromotions, just 1 to 100 micrometers, cause quasi-static fretting. Because there's no full rotation happening, it silently polishes smooth depressions right into the metal without any dynamic impact at all.
Now, because you can't hear electrical erosion, you absolutely have to visually inspect for it. Once the bearing is pulled out, you must apply at least 10x magnification. You're looking for a frosted, matte gray appearance. More specifically, you need to identify corrugated fluting channels. Now, these channels are only 2 to 5 micrometers deep. That is incredibly shallow, which is exactly why the rolling elements pass over them completely silently, until it's way, way too late.
Section 4, lambda ratio and lubricant failure.
We all kind of have this mindset that if a bearing is packed with grease or oil, it's good to go, right? But a bearing can be fully lubricated by volume, yet entirely compromised by its chemistry. Enter the lambda ratio. This is essentially the measure of your lubricant's film thickness against the physical roughness of the metal. If this lambda ratio drops below 1.0, you enter boundary lubrication. The metal surfaces start to touch and smear. But here is the terrifying part about this. That smearing doesn't create distinct clicks or clacks, it just creates a broadband noise elevation that is virtually indistinguishable from the standard background hum of your factory. To the naked ear, it sounds totally normal.
And that right there is exactly why we have to test the chemistry. For your oil analysis protocols, pay extremely close attention to water contamination using Karl Fischer titration. Just 500 parts per million of water can silently slash your bearing's fatigue life by up to 50% through hydrogen embrittlement.
On top of that, a 10% deviation in viscosity means thermal degradation has already compromised that critical film thickness. We've got to start measuring the oil, not just changing it on a calendar schedule.
Section 5. Envelope versus acoustic emission.
So, if we are tossing out the old good ears method, what's the actual instrument playbook we should be using? When we compare our high-end diagnostics, vibration envelope analysis is fantastic. It operates in the 5 to 40 kilohertz range and spots a 0.5 millimeter spall weeks before you'd ever hear it. But acoustic emission, that operates way up in the 50 kilohertz to 1 megahertz range. It catches the ultrasonic stress waves of the crack tip propagating long before a spall even forms. It is so incredibly sensitive that it even works on extremely slow machinery spinning at less than 1 RPM. That's a real game changer.
Let's bring it all together in Section 6, the Predictive Maintenance Protocol. To wrap up this masterclass, let's just look at the overarching physics reality we've uncovered today. The vast majority of a bearing's death, roughly 85% of its lifespan under failing conditions, happens without a single sound. We are completely wasting our time if our maintenance strategy focuses solely on that tiny 15% sliver at the very end.
This reality has to form the foundation of our practical, instrument-first protocol. Every facility manager and reliability engineer really needs to adopt these points. First, implement acoustic emission and envelope monitoring. Second, enforce quarterly oil analysis, making sure you use Karl-Fischer titration and total acid number checks. Third, actively measure your shaft voltages to ensure they stay below that 0.5 volt AC threshold. And finally, cease reliance on manual auditory route checks. Period.
I want to leave you with this final thought. It is time to throw out the stethoscope and completely overhaul our predictive maintenance strategies. The bearing that kills the machine is almost never the one making all the noise. It's the one that said nothing at all. So take a hard look at your current site protocols and ask yourself, are you still listening for failure or are you measuring it? Thanks for tuning into this explainer, and good luck out there on the floor.